Good morning and welcome to this course on partial differential equations. It is an NPTEL video course. This course actually has two parts, PDE1 and PDE2. In the first course we will be doing PDE1, partial differential equations 1, which is a 20-hour lecture, and this will be taken by two of us, myself A.K. Nandakumaran from Department of Mathematics, Indian Institute of Science, and Professor P.S. Datti is a faculty in Tata Institute of Fundamental Research, Center for Applicable Mathematics in Bangalore. So, what in my first lecture I will do, half an hour, we will briefly discuss or describe the material which we are going to cover, not only in PDE1, and we will also explain to you PDE2 what we will be doing it. So, both these two courses together will cover a 1 semester course. So, this first course will be a half semester course and the second one will be another half course. So, totally you will have 40 to 42 lectures covering a basic course on PDE. We will not be covering any advanced course, but because of its nature you need to learn some good fundamentals. So, it is ideal for a master's student, this course, both courses put together will be an ideal course for master's student. So, let me briefly go through it, what we are going to do it in the first 20-hour lecture. So, we will start with some introduction and preliminaries, that is what we are doing it, and this we are planning to cover in 2 hours, maybe 3 hours, but as I said this requires some substantial amount of preliminaries, and I suggest the students who wants to study this course should go through these preliminaries. Since it is a PDE course, we cannot spend too much time on these preliminaries, but I will describe some important aspects of preliminaries. So, first thing is describing PDE1 and PDE2, and that is what introduction. After doing that, the second important thing is about the study of first order equations. We will do it in 2 variables to explain to you the some of the ideas, namely the method of characteristics, and we will explain in 2 variable case to bring out the essential concepts behind it, and that will be separated for linear, quasi-linear and nonlinear equations, and then the higher dimensions we will proceed further. So, through these lectures is not only giving some describing the method of characteristics, we will also try to motivate you the importance of studying solutions of partial differential equations in a non-classical fashion. Perhaps we will introduce the concept of manifold, at least in the case of Euclidean space, and then we do, and this we are planning to cover in 4 hours. After that, as you see, which I will describe today in my second lecture, the importance of classifying PDE in as it is not easy to understand PDE. So, you have to understand the concept of characteristic and non-characteristic Cauchy problems, which will lead to what is called a classification, which we will do it in 2 hours. Once classification is done, we will move on to study the second order equations. Based on the classification, we will have 3 equations basically, and namely Laplace and Poisson equations, which is a class of elliptic equations, which is a representative of elliptic equation. In that we will mainly concentrate on the solvability of Poisson equation. In the process we will introduce what is called the fundamental solution for Laplacian, the importance of mean value property and its equivalence with harmonicity, Green's function and Green's formula, and specifically we will construct Green's function for ball and upper half plane, and crucial step in the solvability not only of Poisson equation and also other general second order elliptic equation. We also derive maximum and minimum principle uniqueness and all that. The another class of equations is the heat equation and wave equation, and in this first PDE1 we will discuss about one day heat equation, that means heat equations in one dimension. We will discuss various aspects of heat equation, we will introduce what is a heat ball, fundamental solution, again maximum and minimum principle, and perhaps solution by Fourier method. And we will also that we will do it in 3 hours, and then we will do it the one dimensional wave equation, we will do the derivation of one dimensional wave equation, D'Alembert's formula, how it is different from Laplace and wave by the nature of solutions, propagation like finite speed of propagation, characteristic parallelogram, Duhamel's principle, equations in finite and semi-finite, semi-infinite intervals, notion of a weak solution, again trying to tell you the importance of studying non-classical solution. This is what we are planning to cover in our this PDE1 course consisting of 20 hours. In the second part, let me briefly tell you, I will not do it in the. So, we will study little more elaborate way whatever we studied in PDE course 1. This is the PDE course 1, this probably may be offered next year in 2022 or maybe in the later second half of second semester of 2021. Okay. There we will study 2 important equations, namely Hamilton-Jacobi equation and conservation law. Both are first order equations. Let me warn you, we can only touch some minimal aspects of these equations, because Hamilton-Jacobi equations itself you can study as a 1 semester or 2 semester course. Conservation laws you can study plenty of hours, a 1 full semester or 2 semester or 3 semester course, and the amount of literature in conservation laws and Hamilton-Jacobi equations are enormous. And but what we will do, some important aspects of Hamilton-Jacobi equation, namely Hofflach's formula, Euler-Lagrange equation, Legendre transformations, some classical problems of examples, namely catenary, Brachistochrone problem and general minimization problems. And in the conservation law we will introduce the concept of generalized solution and Rankine-Hugenoid condition, Lax-Salinic formula, and some aspects of conservation law, and this will motivate you further to study further on these topics. And then we will come back to Laplace and Poisson equation, which we have already studied in the PDE1. We will study more about it. In the first part we may study various aspects of it like maximum principle, minimum principles, and fundamental solutions and all that. So, and we will try to explain to you some aspects of existence of by Perron's method, and then we introduce Newtonian potential for the solvability of Poisson equation. We introduce another important class of functions and some subtleties about studying Laplace equation, and we introduce the concept of Helder continuous functions, why the importance of Helder continuity, and then some weak formulation we try to explain what is called the modern method, Hilbert space method and weak solutions and all that. And similarly we will go further on multi-dimensional heat equation. One dimensional heat equation you already studied in the first class and first course, and then we will do the solutions in higher dimensions, uniqueness, inhomogeneous equations and all that. and similarly multidimensional wave equation. There you will see that subtle difference, the important difference of solutions in 3-dimensional wave equation or and 2-dimensional wave equation. More generally you will see the difference in even dimensional equation and odd dimensional wave equation. So, typically we study first the 3D equation using the method of spherical means and then 2D the method of descent, and distinction between odd and even dimensions, telegraph equation, Euler-Poisson-Darboux formula. We will also introduce what is called the Huygens principle and maybe some concepts about the general hyperbolic equation. We try to study one of the classical existence theory, what is called the Cauchy-Kovalsky theory. Maybe we will introduce the concept of analytic functions and then analytic solutions with analytic coefficients, Holmgren's uniqueness theorem, probably more little about, if time permits, we will do the fundamental solutions of general differential operators. After that, maybe a quick discussion about the introduction to modern weak solutions, and the whole PDE for the last 50 to 70 years is studied based on this modern concept, which requires a larger amount of functional analysis. So, we will not be able to cover extensively about the weak solutions. What we will be doing is a brief introduction to motivate you to study PDE in a more general setup. Okay. So, this is the brief about our course, 2 courses, the first course on PDE 1 and PDE 2. So, let me give you some references. So, let me briefly tell you our aim is to essentially cover our recent book on partial differential equations, classical theory with a modern touch. This is a complete published under IIC Press series. It is recently published in 2020. We are not sure we can cover the entire syllabus, entire topics in partial differential equation, but I am sure in these 2 courses we will try to finish some 70 to 80% of the material mentioned in that, and that will prompt you to study all the material thing. And this is our previous course which we have given, again it is there as an NPTEL video course on ordinary differential equations. This may be useful for some prerequisites, not all prerequisites. There is a video course and there is also a book on ordinary. So, our main reference is the recently published book by myself, 2 of us who is giving this course, and partial differential equations. And there are plenty of references given in our course in our book. So, you can refer, there are many books to refer, there are many good beautiful books. So, one of the few references I have given, L.C. Evans partial differential equations, Fritz-John, these are all some classical references which you already know it probably. And McCowan, and there are Pinchover and there are many books. So, you whichever you found it suitable you can cover that. So, for the prerequisites, as I said, you will soon see probably in the 3rd lecture or something. We will do some prerequisites in 1 or 2 hours, that means from 3rd to 6th half an hour lecture schedules, and what you have to understand is some multivariable calculus, and then you have to understand some Fourier analysis if necessary, not too much, and then you also need to know about the surface measure and surface integration. This is a very important deep concepts, because in a PDE you will be dealing with partial differential equations in a bounded domain and boundary value problems. So, how do you interpret the boundary values, how do you integrate functions on the boundary, how do you introduce a appropriate measure to integrate, because you need a measure to integrate. all that basics you have to. Definitely, as I said, it is not possible to cover all these things, but we give some glimpses of what you require to study. And there are other books like Rudin you can see, and then GB Follen, and our last book is a reference if you want to know more about the ODE concepts. Now, so let me tell you, so little bit let me start with the course now. So, what I am going to do it we will start with this little bit, we will explain to you more. So, let us put at one of the important thing what we require is a multi-index notation. So, let me give you multi-index notation. So, let me fix. So, this is normally this will be for throughout the course we follow omega subset of Rn a bounded open region, bounded open smooth set. You can talk about smoothness in different ways, but let me not get into all that. So, this is where. So, a typical point will be denoted by x is in omega. Okay. So, that means later we will not repeat this again, we will write x equal to x1 etcetera xn. This is what we generally follow, but we for the convenience we will also write here like this. This is for the convenience, okay. But so it is basically transpose, but we will try to write that one. So, you have to understand when I write x, either write it as a column vector, it is considered as a column vector, but we always write it as a for the convenience of writing. Okay. So, this is how you put that. Then for a multi-index alpha, alpha is a multi-index. So, it is a multi-index. What is a multi-index? Where alpha consists of non-negative integers, okay, alpha I, where alpha I is equal to 0, 1, 2, 3 etc. Okay. This is right. So, this is basically in n power n union 0, you can use that one alpha. And with that we will define mod alpha, please keep this in mind, summation. So, I equal to 1 to n alpha I. This is to make your partial differential operator in a very convenient way. So, if you have an x, I will you can define x power alpha is nothing but x1 power alpha 1 into etcetera xn power alpha I. Okay. So, you use this notation. You can also have your operator d by dxj. This we will put it in this notation, we use various notation. So, you use this notation sometimes. Okay. We also use this notation dj, all it will be the same for us. And the more important thing is that you can also put d power alpha. What is d power alpha? D power alpha is the derivative, you take the derivative up to mod alpha times. So, that is advantage of putting this multi-index notation. So, dx1 power alpha 1 etcetera dxn power alpha n. Okay. So, you can also put dj power whatever it is wanted. So, use these notations. So, d power alpha sometimes we also use it. So, if you read different books, people use different things. So, you can actually use this notation. Okay. So, that is the about the multi-index notation. So, keep this in mind, there is nothing complicated about it. This allows you to write my derivative in a very convenient way. So, we will do that one. Okay. Okay, we go to the next page. So, let me write down. So, what is a kth order differential operator equation? Kth order differential equation. So, it is a relation. So, there will be an unknown function u equal to u of x is an unknown function. Unknown function. Okay. So, let me delete this. Okay, unknown function. So, it is a relation, the relation is considered as a function which is variable. So, you can write anything and you have the derivatives of order alpha and that order goes up to mod alpha less than or equal to k. So, the up to kth order derivatives, at least one kth order derivative appears, then it will becomes a kth order PDE. This will be equal to 0. So, we can also write it in a slightly different way. Same way, there will be certain terms in f which will not have the unknown. So, when you have some terms in the f in that expression and you take all these unknown, that is called the homogeneous term, non-homogeneous term. So, collect all the non-homogeneous terms and put it on the right hand side. So, another way of writing, it is not exactly another way, this is to explain a notion of linearity u d power same thing modulus of alpha less than or equal to k, that is of the form some non-homogeneous term. So, you see, so whenever you have an isolated term in this first expression, and you take it and in this expression there are no non-homogeneous term which is taken to the right hand side. So, f is some function, you can see that f is some function, it maps from some Rn or in some domain omega, this not or this may be in some domain omega. Okay. So, you have it can be an Rn also, that is for the x variable. Then you have your u is an unknown function. So, u mapping from some omega to Rn, okay, and it is a real valued map. So, you have your u from omega subset of Rn to Rn, this will be some r. Then you have some alpha, it depends on how many terms they are coming. So, it may be some RL for some L, okay, for some L depending on how many terms of, we will come to little more when you write it first order equations. So, that is the way your first order equations are written, not first order equation, a general PDE of kth order is written like that. So, what I want to describe is what is a linear equation. So, quite often why I am explaining this is what we have noticed from our experience, most of the students know how to recognize a linear equation and nonlinear equation, but then students generally have difficulty of, if you ask what is a linear PDE. Okay. I want to clarify not only how to recognize a linear PDE, what is this linearity to do with the linear algebra linearity, is it something different, and then we will also explain quasi-linear. After that you of course you have non-linear. In general all these equations are non-linear. So, you have all that. Okay. So, we will go to the next page. Okay. So, linear PDE. So, we are looking at the linearity, look at this function f x u du d power alpha of u with mod alpha less than or equal to k. You look at this thing. What we are asking for for each x. So, f can be viewed as a mapping. So, f can be viewed as a mapping, fix x, then f can be viewed as a mapping for all these variables from R cross some RL which I told you to R. Then we want the linearity of, then we need linearity of this map. That is a one way. There is another way of seeing it. Of course, you are basically looking at the linearity of these two, and that you have a collective linearity. Okay. So, this need the linearity of these things. Then from linearity, from linear algebra, you can have a form. Whenever you have a map in a Rn, then that can be identified as a dot product basically. Okay. And when you have a linearity looking for each x, when you that vector will change it, that is all, because you can identify it with, because whenever have a linearity it has to be a Rn, every element can be identified with a element from Rn. So, using that linear algebra, those who are not familiar, leave this, I leave it as an exercise. Those who are not familiar how to write this linearity, then this exactly tells you, you can write this f of x u d power alpha of u less than or equal to k. You can write this as a map from here, sigma a alpha of x, okay, your d power alpha of u, okay, x mod alpha less than or equal to k. Yeah, let me tell you one clarification. Actually, you do not have to include this u here or u here, because when I take alpha equal to 0 0 0 etc., you will get d power 0 of u, that is nothing but u. Okay. So, it is up to you how you want to write it. So, basically alpha equal to 0, it comes here. So, you have this here. So, you do not have to add even this term. So, the general equation actually can be written in this form. Okay. I only separated it, nothing wrong the previous way of writing, but this is the best way of writing. Okay. Mod alpha less than or equal to k, you have mentioned, because when mod alpha equal to 0, you get d power 0 of u, now that is nothing but u, and you get back this term. So, this is what you can write it. So, from linear algebra, that is why. So, you can recognize now, at the moment you are given an equation is given, the all the unknown u and all the derivative u of u got separated now. So, there is no mixing, no non-linear function of u, nothing you will see, it is all got separated out. So, I will stop here and then I will continue these linear equations, and then I will explain to you non-linear quasi-linear equations. After explain to you the quasi-linear equations, I will write more specifically about your linear equations and quasi-linear equations in two variables, how you can very precisely write it which most of you are probably familiar when learn the beginning of your PDE course. So, we will see you in the next class. Thank you.